Sometimes in quality control of manufacturing process, it's a lot easier to, rather than do, say, direct physical measurements of a part that you're producing, you can instead pass it through a template. And so it becomes a binary type of thing, or binomial type of situation. Either it absolutely is okay or it absolutely is not. And shades of gray are not particularly all that important. In such situations there, now you're going to be calculating proportions or total numbers of non-conforming or defective sorts of units that you're dealing with. And so here with the P charts, we're really focused with a proportion, and you might consider this to be defects, but remember it could be more generally non-conforming as opposed to just only defects. Right? And so in the P charts here, we're going to let D be the number of non-conforming or defective units in a sample size of N. So if it's, say, a number of ball bearings and they have to pass through a template rather than taking the actual measure of the diameter of the ball bearing, then we've got N of those and how many of those turn out to be defective. And then, so our particular proportion that we're dealing with is a straightforward calculation, D divided by N. And following along our binomial path, then our variance of our proportion will just be equal to P times 1 minus P. Remember, we sometimes call that Q for shorthand, and then divided by N, our sample size. Right? And so a P chart then will establish our upper and lower control limits back down on P plus or minus, and if we're still doing the 3 sigma approach, then 3 times the square root of P times 1 minus P all over N. Right? And now if we have a process situation where we have many subgroups that we've collected data from, then our P bar from that is going to come from then the arithmetic average off of our individual subgroups. Right? And since each of the individual piece of i's are given to us by the di's over n, and presuming that we have the same sample size in each and every case, we generally would, then, and if not, then you can deal with that, but generally you would have the same. And so that constant could be pulled out, and so you get P bar being equal to the 1 over m times n, and then just sum up the total number of defects that you've got. And then the P bar becomes your estimate of your actual population values, and then you can substitute that directly in to obtain your upper and lower control limits. Now, this relies upon the normal approximation to the binomial distribution, right? So when P is small, the normal approximation may not always be accurate. So if P is small, then you can change this and use the binomial probabilities then to do the calculation of your control limits. The other thing here is if LCL turns out to be less than 0, then go ahead and use 0. There's no practical significance for a lower control limit that's less than 0. Okay. A similar and related chart to the P chart is the U chart. Where here we're looking at number of defects per unit. Right? And as soon as we start thinking about here number of defects per unit, you ought to be thinking about the Poisson distribution and its single parameter of lambda coming into play. And so here in this situation then we've got C being our total defects in the sample, right? And the sample size here is n, and so our u value is going to be c over n. Looks very similar, right, to what we were dealing with before. But because it's a Poisson kind of situation here, right, that we need to think about that u sub I is our single point that we're plotting on the chart, and that this u sub I in itself is an average, right? If we go back to the Poisson distribution here for a moment, it has this parameter lambda, that the mean of the Poisson random variable is lambda, and its variance is also lambda, right? Single variable or single parameter random variable. And so when we go start taking a look at u and those sorts of things, expected value of u is equal to lambda. The variance of u turns out to be, because u is going to be associated with all of these guys, right? Then, because our u bar that we're going to go after, our estimate of our long-term average is going to be the sum of those divided by our m, our subgroup, and we're going to end up with, for our upper and lower control limits, then ultimately something similar to what we saw up above with the p-charts, but we'll have the square root of u bar divided by n times 3 plus or minus u bar. And again, if you want to create those zones, you just go 3, 2, and 1 to create that. And so notice the overall pattern that we continue to end up with here in these control charts, and that is that we center things on our average, right, and then plus or minus, and typically 3 for our control width, 3 sigma, and whatever turns out to be our sigma. And when we start using sample statistics to estimate then what the what the population values are, then we often see that n starting to show up in there. Right, so it's a very characteristic template, so to speak, of how to go about creating these control charts.